Well, I gotta get the right. Yeah, but then it's like a light behind you.
Yeah, well, there's no.
Can't see, but that's okay.
At the back. So that's just start the tennis sheet in the back.
The back of the leg. The back of the leg. Or the basic. So curl, my friend. Like you more.
Good morning, my friend. Shut up, Billy. Is it like the core? Is it like the whole leg?
Like I was doing that thing. Oh, it's like this is your arm.
Yeah. Okay. So did you just tell them?
No, I didn't.
I don't know. I never said that.
I have like that's when I looked over this.
I'm gonna put this up higher. Is this gonna bug you? I don't know how I pronounce it. Futoma? No, tell me how I say it. Fatuma. Yes. Even if you just start here, I'll take it. Fatuma. Yeah. You're trying too hard. Fatima. That's it. Fatima. Okay. Yeah. I went to war. You like my color? And I jumped on my job. I was doing about half time and I hated it. And I said, I met this girl. I'm my MP. And she just met me. And she knew how to say my name. And I hounded her. So that the whole day yesterday, she was calling my whole name.
Really?
Yeah.
She said. It helps because we didn't have medical terminology yet. And our teacher would always like
Susan Jacobs.
And I was Fatimata. It's like it's a freaking word for
I mean, people always think so hard, but it's like there's no word, there's no letter.
Like an iron on your chest. Yeah.
Just off. Because
That's what it's fun of it.
Easy for me to say.
My teacher last year made us all sign a statement stating that was one of my teachers too. We wouldn't use it. How would they be able to tell? Like I'm in my home. Now it's just like I've got lots of people in this one. I can't find my orange one from my other pack. So I had to grab one from here. Because I should have two each color. So then one goes in my colors and then I bring it to it. And then she has like homework, so then I will use and I only got one purple. I'm missing an orange. And green. Oh yeah, that's right. And green. I think I only have one green. Yeah. Oh yeah. And I got another. Oh yeah, I tried that. That didn't work. Press it off. That's done. That's done. Oh yeah, I gotta do that. And that's done. I guess I started record sooner than I needed to. I don't know what the size are. I'll stop it. Oh, I'm 30 right now. Yeah, because I heard about
Alrighty, let's get started. Good afternoon, my friends. Good afternoon. Alrighty, great. Okay, so just want to remind you that on Wednesday we finished our discussion on Chapter 1, and I assigned you a quiz, your first lecture quiz. And that quiz has been opened ever since, and it will close tonight at midnight. All right, so if you haven't taken it yet, make sure you take it. And please do not wait until like 11:50, right? Because if anything goes wrong with Blackboard, things happen, things go offline, all that kind of stuff, right? You've left yourself no room for error, right? That's when you're emailing me, with the sob story. The cat shorted out my computer at 11:55. That's it. It's not the cat ate my homework before, it's the cat shorted out my computer, right? And I have to say, oh, too bad, so sad, you had 3 days. No, usually I'm bleeding hard, and I go, okay, I'll let it go a little longer. Right? But I'm getting harder, and as I get older, I get more from it. Okay?
Chuck, how long did you say the test was open?
I said it was open for 10 minutes. What do you ask?
It's a little longer than that.
Don't share with us.
It might be. Okay. So,
In
it will close tonight at midnight. Right? I will discuss the length of the time allowed for the quiz next week. After it's closed. Right. So make sure you take that first quiz, right? And you should be able to see your answers immediately. What you got right, what you got wrong. Will not give you the answers because I don't want to give you the answers. I want to force you to go, not to memorize the answers, but to go and figure out if I missed that question, why did I miss it, so that I can study and understand what I didn't understand, so that when I have the exam, right, I knock it out of the park, right? That's the thought. Okay.
Attendance sheet.
Attendance sheet.
Yeah, it was in the back.
Attendance sheet. I started in the back, and it's supposed to come to the front.
All right.
Right. Yeah.
It should be coming somewhere.
We'll start at the front, and we'll send it toward the back, and hopefully everybody who missed it the first time will get the check. Okay. Can you see this board? Okay. Or do I need to dim the lights even more? Can I see it? Okay. Okay. Cool. Alrighty. So then we start talking about chemistry, and I think we said to understand physiology, you needed to have a basic understanding of chemistry, because basically physiology is the interaction of atoms and molecules with one another. So you have to, in general, understand or have a basic understanding of chemistry, how molecules behave, how they interact with one another. Okay? We're not going to do calculations and all that, deep stuff that you did in chemistry class, but you do need to understand the concepts, right? So that's what we're going to focus on in the chemistry chapter. Okay? We started talking about energy and matter. We said matter is anything that has space and space and mass or weight. And we said that energy was the capacity to do work, right? Like the capacity to wait tables, clean floors, stuff like that. That kind of work, right? Right. No. Right? So what is work?
Moving matter.
Moving something. Moving matter, right? I'm doing work by moving this pen. Right? I'm doing work here because I'm moving something, right? So energy is the capacity to move something. And we said that energy can be stored, right? Potential energy, right? Like this pen sitting here on this has the capacity to fall, right? So it has potential energy, and then as it's falling, that potential energy is converted to kinetic energy, energy of motion, right? We talked about the different forms that you can find energy in. Mechanical energy, where this energy involved in directly moving something, right, like pedaling a bicycle. Radiant energy, energy of the electromagnetic spectrum, like ultraviolet light, X-rays, visible light. Then there's chemical energy, right? All of us eat food to get the chemical energy out of it, right? The energy that's found in bonds. Electrical energy, where you have a separation of charges. Maybe you have a lot of positively charged, well, we'll go to a battery, right? You have a battery, right? You'll have a separation of charges where you have negative charges, abundance of negative charges on one end, and abundance of positive charges on the other. And if you connect them with the circuit, right? Negative charges flow from one end to the other, right? You can take it through, say, a light bulb, right? Don't ask my light bulb, right? And you can convert that electrical energy to light energy, okay? Energy can be energy is never created nor destroyed, but it can be easily converted from one form to another, right? Here, electrical energy is converted to light energy, right? But in the process, some energy is lost, typically as heat. And anyone who's touched an incandescent bulb when it's been on for a while, right, you can certify that heat is produced and energy is lost as heat as energy is converted from one form to another. Okay? And the same thing happens in the human body. Where do we get almost all of our energy? We get it from the food that we consume, right? So we consume quarter pounder of cheese, right? Fries, and Coca-Cola. What a meal that is. Right? We consume all that chemical energy, then our bodies break it down, absorb it, and eventually convert it to ATP. ATP is the energy currency of the body. Right? It's what our cells actually use to do work, to move things. Right? So our body converts food, chemical energy in the form of food, to ATP, and then our cells can use ATP to do work, to move substances across the plasma membrane, which we'll talk about when we get to the cell chapter, to contract a muscle so you can pedal a bike, right? Or hit your brother upside the head, or to run metabolism, right? Breaking bonds or forming larger molecules from smaller molecules, all right? And just like in the light bulb, where energy is converted from one form to another, heat is lost. Also, whenever energy is used to perform some type of work, some heat is lost in the process. That's why the more physical activity you do, the more heat your body produces. Because as you do physical activity, your body uses more ATP, and a byproduct of that use of that energy is heat. Okay? And that is where we left off on Wednesday, right?
Yep.
All right. Okay. Let's move on forward. Now we basically discussed all we're going to discuss about energy, at least for right now. And we're going to focus on matter. Again, anything that has space and has weight. Okay? So we're going to define what an element is. List the four elements that make up the bulk of the human body. Explain how elements and atoms are related to one another. Then we're going to look at the subatomic particles, the electrons, the neutrons and the protons. We're going to talk about their charges, where they're found, and talk a little bit about their relative masses. Okay? So we said that elements are the fundamental units of matter. All right, the fundamental units of matter. I think I use as an example. Where's the eraser? Oh, with you. Right? You could break all matter down into pure substances, substances that can not be broken down into simpler substances by chemical means. So you could take something simple like water, which is H2O, oxygen, and hydrogen, and you can break it down into hydrogen and oxygen. Right? And before anybody says anything,
There you go.
I'll balance the dead burn equation. Okay?
Thank you.
Okay? So you can break it down into elements, hydrogen and oxygen. But you can break it down no further, not chemically. Okay? All matter composed of about 112 elements. We list those on the periodic table. Okay? And there is a periodic table at the back of your book. All right? Don't stone me if it's not exactly that page. Right? Because I keep changing the versions on you. Right? So maybe a little. That may not be the exact page, but it's in Appendix B at the back of your book. Okay? Now, despite the fact that there are 112 elements that we know with certainty, there are 4 elements that make up more than 96% of the human body. 96% of the human body is composed of only 4 elements: carbon, oxygen, hydrogen, and nitrogen. Okay? Carbon, oxygen, hydrogen, and nitrogen. Now, I do want you to know that. Okay? I do want you to know that. Okay? We can add just a few more elements, and we will be able to, and we'll get the 13 elements that make up over 99% of the human body. Now, to me, that's quite amazing. Out of 112 elements, 13 represents almost 100% of the human body, right? And I am not requiring you to know this. All I want you to make sure you know are the top 4. The 4 elements that make up 96% of the human body. But for those of you who are going into medical or biological fields, it might be good to go ahead and be able to list or to be familiar with the 13 elements that make up almost 100% of the human body. And I have a nice mnemonic device that I learned when I was in college, a freshman in college, with this one. C. Hopkins Cafe. Mighty good and naturally clean. Right? Carbon, hydrogen, oxygen, phosphorus, potassium, iodine, nitrogen, sulfur, calcium, iron, magnesium, sodium, and chloride. C. Hopkins Cafe, mighty good and naturally clean. Those 13 elements make up more than 99% of the human body. And for the most part, life, period, any living organism. Okay? Not just humans. Okay? Again, not requiring that you know that, but might be helpful for those of you going into biological and medical fields. Because you're going to run into those elements over and over again. Right? And you need to know them. You need to know their chemical symbols as well. Okay? So let's talk about the basic unit of matter. Right? So the smallest amount of an element that you can have is an individual atom. Let's talk about that atom. Let's basically look at the anatomy or the structure of an atom. So you have a nucleus, which represents the center of the atom. And it's composed of two what we call subatomic particles. It is composed of protons, which are shown here in, I guess that's sort of orange. I guess that's orange. Shown here in orange. And protons have a positive charge. That means they are attracted to negatively charged substances. We also have in the nucleus, neutrons, shown in yellow, and neutrons have a neutral charge. That means they are neither attracted to nor repelled by other charged particles. Okay? And those two subatomic particles are found in the nucleus. We also have outside of the nucleus subatomic particles called electrons. They're considerably smaller than protons or neutrons, and they're negatively charged, meaning that they are attracted to positively charged particles. And these electrons sort of orbit around the nucleus, right, much the way a satellite orbits around the Earth, right, attracted to the positively charged protons. Now, most of an atom, believe it or not, is actually open space, right? It's actually open space. If this atom were, say, Camp Random, right, these protons and neutrons could be represented by marbles sitting on the 50-yard line in the middle of Camp Random. All right, so most of an atom, believe it or not, is actually open space, right? And then you could have a few, I guess, grains of salt up in the stands, moving around through the stands, could represent the electrons. So most of an atom, believe it or not, is actually open space. Now, sometimes you'll see atoms represented like this, which is called a planetary model, right, where it's shown very much, the electrons are shown very much like a satellite orbiting around the nucleus. Other times you'll see them shown in this what's called an orbital model, where instead of showing the individual electrons, it's shown as an electron cloud. And they do that because theoretically at no given time can we predict where an electron specifically is. We can just have probabilities of where you would find one at any given time. So they use darker shading for where there's a high probability of finding electrons at any given time, lighter shading where there's a lower probability. All right. I'm not going to ask you about orbital models and planetary models. I just explained this so you see orbital model or planetary model, you have some idea what am I looking at and why do they show atoms different. Okay. What's important to know is the subatomic particles, their charge, and where they found. Okay. Okay, so every element has a unique atomic number. It is the number of protons that element has. And if you look at the periodic table, the elements are arranged by atomic number starting left to right. All right, so if you look at hydrogen on the top left, it has one proton. That's its atomic number. Then you go over to the right side, helium. That's its atomic number 2. Come back to the first group there, and lithium is 3, and then beryllium is 4, and so forth and so on. Right? If you read left to right, the atomic numbers increase. Okay? It's the number of protons. By definition, it's the number of protons that an atom contains. A neutral atom contains the same amount of electrons as it does protons, right? So you can look at the atomic number for an element. Not only do you know the number of electrons, but you also know the number. Not only do you know the number of protons, but you also know the number of electrons that it has. But by definition, the atomic number is the number of protons. Okay, we can describe the weight of a atom by counting the number of protons and neutrons it has, because the protons and neutrons are much larger than the electrons. So we say that a proton and a neutron has 1 atomic mass unit, and the electron is somewhere like, it's like a 1/2000th the size of an, is it 200th or 2000?
I think it's like 1800.
Okay, 1800, 2000. It's like 1/2000th the size of a proton or a neutron. So we pretty much just disregard it when we talk about the atomic mass number. Okay, so atomic mass number is pretty much number of protons plus the number of neutrons. Now let's talk a little bit about isotopes. So you can have different varieties, shall we say, or I should say different atoms of the same element. You have atoms that have different neutrons, different numbers of neutrons, but yet have the same number of protons. Right? In the case of the element hydrogen, for example, most hydrogen is in this form, right? This isotope where it has 1 proton, no neutrons, and 1 electron. But a small percentage of hydrogen exists as the isotope deuterium, where it has 1 neutron in addition to 1 proton, or as tritium, where it has two neutrons in addition to 1 proton. All of these atoms are of the element hydrogen because they have the same number of protons. But they differ in the number of neutrons. Therefore, their atomic weights are different. Okay? Or, excuse me, their atomic mass, I should say, are different. All right? Here, the atomic mass is 1. Here, it is 2. Here, it is 3. Okay? Do you see this? The atomic weight for the element is a weighted average of all the different forms or isotopes of hydrogen. Right? So if you look on the periodic table, you'll see the atomic weight is pretty close to 1. It's barely a smidget greater than 1. And that's because like 99.9% of hydrogen is in this form. Right? And a small little bit is in this form and this form. So when you take the weighted average, you get something that's a little higher than this. Okay? All right, you're looking at me like, this is all very nice, but I don't understand a word you're saying.
No, that's fine because I'm kind of feeling like that.
Anyone? That's what you're having issues with?
Yeah.
Oh, no problem. All right. So you have 3 different, let's say, varieties of hydrogen. Right? By definition, a hydrogen atom has to have the same number, has to have 1 proton. Because if you look on the periodic table right above the H is a 1. Okay? So this is a hydrogen atom, right? This is element hydrogen. This is the element hydrogen. This is the element hydrogen. Where these 3 atoms differ is the number of neutrons. Okay? This one has no neutrons. This one has 1. This one has 2. They're all hydrogen. They're all of the element hydrogen. And they behave the same way. This will form water with oxygen. This will form water with oxygen. This will form water with oxygen. But because they have different numbers of neutrons, they have different atomic masses. Because the definition of atomic mass is protons plus neutrons. Okay?
So where would you find the other two isotopes? I mean, why do you have different isotopes of hydrogen?
That you would have to ask a chemist that.
All right.
That I do not know. It's atoms that have the same number of protons. They have different number of neutrons. All right. What's more of an issue for people to understand is the atomic weight, because I don't understand that. That's usually where students run into challenges.
Is the weight the proton plus neutron plus electron, and mass is just proton plus?
No. Mass is for the specific atom.
Okay.
So this is the atomic mass. This is the atomic mass for deuterium. This is the atomic mass for tritium.
Okay.
But the element hydrogen exists in all three of these forms.
Right.
Right? Mostly as this, but a small little bit as this. So when you take the weighted average, that is, if you take 99.9% times 1, and then the other 0.00001 times that and that, you get this number, which is slightly above this.
Okay.
Right? Make sense? Right?
So are those the only hydrogen isotopes?
Are those the only isotopes of hydrogen?
Yeah.
As far as I know. If there's some very, very, very small other isotopes I'm not aware of. And probably the only time that you'll ever run into these isotopes will be if you go into research. Sometimes they will use these different isotopes here in administering certain chemicals and stuff to people, and then because they have different weights, they have devices that can track them, right? And you get into tissues, and then you can assay the tissues for water, for example, tritiated water versus your standard water, right? That's really the only place that you're going to run into this, right? But if you hear the term isotope, you should at least know, right? As educated college students, right? You should at least know what it means. All right, same element, different numbers of neutrons. Okay. Now, what you probably are more familiar with, what you probably heard, what you're probably more familiar with is the term radioisotope. Okay, here you have a form of a atom that is actually radioactive. I mean, it's unstable, it's breaking down, and it's emitting some subatomic particles, electrons and or protons, right? Those tend to be very heavy isotopes, right? And they're decomposing to become more stable. Right? They're going through a process of what's called spontaneous radioactive decay. Right? Now, why do you care? Well, as medical practitioners or future medical practitioners, you may run or you may use some type of radioactive isotope, right, in diagnosing or treating disease. Okay? There is some information about radioisotopes in your book, right, under a closer look. I'm not going to require that you know anything about radioisotopes, okay, in terms of testing or whatever, but if you have an interest in it, there is information in your book under a closer look. It's used sometimes for CT scans where radiation will be the body will be bombarded with radiation, and some substances take up the radiation differently than others. And if you have a medical device that can detect that, then you can, for example, detect a tumor. You also can tag certain substances with radioactive isotopes. For example, you can take glucose, which is what you know as blood sugar, or you can incorporate radioactive, I think it's carbon, into glucose. Glucose is C6H12, O6. Each molecule of glucose has 6 atoms of carbon, where you can use a radioactive form of carbon. So if you have a radioactive glucose molecule, you can administer that to a patient, put it in their blood. And anything that uses a lot of glucose, consumes a lot of glucose, like brain cells, will take up a lot of that radioactive glucose. And then if you have a device that can detect radioactivity, you could monitor the glucose consumption in different parts of the brain. All right? And why would you want to do that? Well, if you want to see, what parts of the brain are responsible for what types of activities, right? You could administer that radioactive glucose, monitor the brain, and then administer certain tests to a person, like make them laugh and see which part of the brain is involved in laughter, right? Whatever part of the brain is involved in laughter, it'll use a lot of glucose to make energy. Or long-term versus short-term memory versus any activity, right? You can administer a test and then look and see what parts of the brain are using a lot of glucose. All right, so those are just a couple of the functions or uses of radioisotopes in medicine. Again, I'm not going to require that you know them. Okay. Alrighty, so any questions about the basic anatomy of the atom? You understand that the atom is composed of electrons, neutrons, protons. You know the charges of each of those subatomic particles, and you know where they're located, right? You can draw an atom and label on it, right? Okay? Cool. It's important to know that in order to understand bonding, okay, which is what we're now going to talk about. Okay, so we're going to talk about how atoms and molecules interact with one another to form chemical bonds. We're then going to define what a molecule is, what a compound is, all right, and identify some examples of each. Then we're going to talk about different chemical bonds and chemical reactions. We're going to discuss ionic bonds, covalent bonds, both polar and nonpolar. We're also going to mention hydrogen bonds. We'll come back and talk about hydrogen bonds in more detail. If not today, definitely on Monday. And then we're going to look at the 3 main types of reactions: synthesis, decomposition, and exchange reactions. Okay, does that sound like fun? Mm-hmm. All right. Okay. Molecule, 2 or more atoms that combine chemically. All right. So a hydrogen atom meets another hydrogen atom. How you doing? Right? They interact, form a bond, and form molecular hydrogen. All right? So a molecule is 2 or more atoms combined chemically. And when we say combined chemically, it means a bond is forming between them.
Is it the same? It has the same atoms.
Nope. Molecule doesn't have just 2 or more. Okay. Period.
Okay.
Right? 2 or more. Right? By the way, the hydrogen gas that we're all breathing in is in this form. Single hydrogen atoms are not very stable, right? So hydrogen gas is in this form, H2. That's what's called molecular hydrogen. It's a molecule. All right? Everybody good? Mm-hmm. All right, cool. A compound is 2 or more different atoms combined chemically. So there's a special type of molecule. All right? So here you have 4 atoms of hydrogen reacting with an atom of carbon, which forms CH4. Does anyone know what CH4 is, by the way?
Methane.
What?
Methane.
Methane, right? Or what the English call methane, right? CH4, okay? It's a compound because we have 2 or more different atoms. We have carbon and we have hydrogen, 2 different. Here, we had 2 atoms that are the same. All right? So here we have a molecule. Here we have a compound. Now, here's a question for you. Is CH4 a molecule? Yes. Why?
Because there's 2 or more atoms.
Right. It's 2 or more atoms. All right? To be a molecule, you have to have 2 or more. Doesn't matter. They can be the same. They can be different. 2 or more. Period.
Yeah, it's
Compound is a special type of molecule.
So would you call it like a molecular compound?
No, because by definition, the compound is a molecule. You can have a molecule without having a compound, but you cannot have a compound without having a molecule. Right? So a compound is just a special type of molecule. Okay?
So if there was a question that said, what is CH4, could you answer either or would you prefer that we answer compound because they're different?
Well, I mean, I never asked an open-ended question like that, because you can say, well, it's a compound, it's a gas, you can say a whole lot of stuff, right? But what I could do is say, which of the following is a molecule, right? And then list a whole bunch of stuff, and then when I say, or all of the above, and it had to be, if it had more than one, they all had more than one atom, it had to be all of them.
Okay.
Right?
All right.
Okay? Let's do a few others. All right. See if you're catching what I'm flinging. Right. All right. This is water. H2O. Is it a molecule?
Yes.
Yes. Is it a compound?
Yes.
Yes. Right. It is a molecule because two or more atoms. It's got three. Right. 2 hydrogens, 1 oxygen. It is also a compound because it contains 2 or more different atoms, right? What about O2? Compound?
No.
Molecule?
Yes.
Yes, because it's got 2 oxygens, right? What about C6H12O6?
Yes.
Molecule?
Yes.
Compound?
Yes.
All right. Bye, George. I think they've got it. Okay? Now, when atoms interact with one another chemically, they form bonds. Right? When atoms dissociate from one another, right, bonds are broken. Okay? Bonds are broken. And by the way, what is happening naturally is, atoms are always in motion. Right? And when atoms run into one another, bonds are formed. And in other cases, when molecules run into one another, bonds can be formed or bonds can be broken. All right? But what's happening is molecules and atoms are moving about. All right? Running into one another, reacting, forming bonds or breaking bonds. Okay? Let's now talk about how bonding occurs. Okay? We're going to focus on electrons because electrons are the only subatomic particles that directly are involved in bonding. Okay? Specifically, the outer shell electrons, or the electrons that are on the outer shell, or what's called the valence shell. Okay? So electrons occupy a certain space outside of the nucleus called an energy level. Okay? So this particular atom is neon. Right? This first energy level can hold at most 2 electrons. The second energy level can hold at most 8 electrons. Okay? Yes. That is true for everything. Okay? What's important is that not necessarily that you know how. I'm not going to ask you how many electrons a particular energy level can hold. What's important is you understand that there is a maximum number that they can hold. Okay?
How many levels are there in each?
Bunches.
Forever? Infinite?
No, it's not infinite, right? Basically, you can look at the number of horizontal rows you have, and that basically tells you how many energy levels each atom of each element has. Okay. Right? Like hydrogen and helium, right? They have 2. They have 1. They have 1 level. They have 2
electrons each.
Hydrogen has 1 electron. Helium has 2. Right? This first level can only hold up to 2. Right? So once you get 3, you have to go to the second one. If you look, the second period there, lithium, beryllium, right? Okay.
Is that why hydrogen's not stable? Because of the missing electrons?
Right. Yeah, you're getting ahead of me. Don't go there yet.
Oh, sorry.
Don't go there yet. All right. Just understand that only each energy level can only hold so many electrons. Right. But you're getting it. Okay. Also, FYI, the closer the electrons are to the nucleus, the more tightly they're held because of the positively charged protons in the nucleus. Okay? So each energy level has a maximum number of electrons it can hold. Helium, for example, can hold, first energy level can hold at most 2. That's why if you have a 30 electron, you have to go to the next level. That's why lithium, beryllium with 3 and 4 electrons respectively, you have to go to the second energy level. The second energy level can hold at most 8. Right? The energy levels follow the rule of 8s. Right? Well, the first one follows the rule of the duet rule. Right? It can hold at most 2. Right? The next energy level 2 and 3, although not shown here, can hold at most 8. Okay? Now, why is this important? Well, atoms want a full outer shell to be, in order to be stable. Okay? They want a full outer shell. Right? If they have a full outer shell, they will not react with other atoms. Okay? If they have a full outer shell, they will not react with other atoms because they're happy. Right? Helium has 2 electrons. It has a full outer shell because that first shell or energy level can hold at most 2 electrons. So it's not going to react with anything. That's why you've never heard of the substance helium chloride or helium oxide or helium anything because it's not going to react. Right? It's happy. It says, another atom comes along and goes, no, I'm happy, go away. Right? The same thing with neon. Neon has 10 electrons. The first 2 inhabit the first energy level or shell. The next 8, the second one. This shell can hold at most 8. It has 8. It's happy. That's why you never hear of the compound neon chloride or neon oxide or neon anything. Because it will not react to another atom. So,
Those noble gases?
Yes, those are the noble gases over this last period here where you say helium, neon, last group. We have helium, neon, argon, krypton, xenon, and radium, I think. All those have full outer shells, so they do not react to other atoms, and they are called noble gases. Right? But they're noble, they do not react to other atoms. Right? But most atoms, basically all the others, do not have. Oops, sorry. That was last semester. Sorry, you didn't see anything. All right. Most atoms do not have a full outer shell, and so they're going to react with other atoms in order to get a full outer shell. For example, hydrogen has 1 electron in its outer shell. What does it want? It wants 1 more, so it'll have 2. Then it'll be happy. Right? Carbon has 4 in its outer shell. How many does it want?
8.
It wants 8. Okay? So it wants 4 more. Right? Right? Like Obama, 4 more years. Right? Oxygen has 6 electrons in its outer shell. It wants 8, so it wants 2 more electrons. Okay? And sodium has 1 electron in its outer shell. It wants 8, so it wants 7. It wants 8 in its outer shell. Okay? So these atoms are going to react with other atoms in a way that gets them a full outer shell. Okay? So they will donate an electron, they will accept electrons, or they will share electrons in order to get a full outer shell. What do you think sodium is going to do to get a full outer shell?
Give it to hydrogen.
It's going to just give up 1 electron, then it has a full outer shell, and it's happy. Right? What about oxygen? What do you think oxygen will do?
Gain. It took 2.
Oxygen usually will share, right? Like oxygen will share with hydrogen, right? With 2 hydrogens, so it gets 2 electrons, and hydrogen gets hydrogen gets 1 electron. It just shares 1 pair. Okay. What about carbon? What do you think it's going to do? it's going to share also, right? It's not going to give up 4 electrons. Are you kidding? I'm going to give up all my electrons, right? It's not going to take 4 electrons. It tends to share. Okay? No, I do not expect you to memorize that. What I want you to do is understand the concept. Why do atoms form bonds? Because they want to fall out of the shell, and so they will react with other atoms in order to get it. Okay? When atoms react with one another to form a molecule, and one atom donates an electron to another atom, an ionic bond is formed. Right? And I have a video, I hope, that will illustrate that.
Sometimes atoms complete their outer shells by gaining or donating electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons, but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom is called an ion, in this case, a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Okay, so let's go back before they form the bond. So here you have sodium. It has 1 electron in its outer shell. Here you have chloride. It's got 7 electrons. It wants 8. So sodium is going to give up or donate 1 electron to chlorine. Now sodium has a full outer shell, and chlorine has a full outer shell. However, now for sodium we have 1 more proton than we had electrons, because it gave up an electron. It had the same number because it was a neutral atom, then it gave up 1 electron. So now it has more protons than it had electrons. So now it is no longer an atom, but it is a positively charged ion. And a positively charged ion is called a cation. Right? Now chlorine has 18 electrons but only 17 protons because it gained an electron. So it has more electrons than protons, and so now it has a -1 net negative charge. Now we have 1 positively charged ion, 1 negatively charged ion, and by the way, we call the negatively charged ion an anion. So they are, because they have opposite charges, they are attracted to one another. And that, in essence, is the ionic bond. The ionic bond is not necessarily a physical connection. It's a relationship. Okay? And this new compound that's formed has its own set of properties. Right? This is table salt, sodium chloride. Right? It has its own set of properties, irrespective of its components. Sodium is toxic, and it's a solid. Chlorine is a gas, and it's also toxic. But sodium chloride is a solid, and it's not toxic. Right? Relative. Okay? It has its own unique properties. Okay? Now, any compound that's formed through ionic bonding is called a salt. All right? Any compound that's formed through ionic bonding is called the salt. Sodium chloride is what we call table salt because we put it in our food, right? But potassium chloride, hydrogen chloride, magnesium oxide, sodium fluoride, all of those are salts because they are compounds formed through ionic bonding. Okay, sometimes atoms will share electrons. And when atoms share electrons, a covalent bond is formed. And you can have the sharing of one pair of electrons, which is a single covalent bond, or two pairs of electrons, which is a double covalent bond, or even you'll run into triple covalent bonds, but they're relatively unstable. Okay? So here, back to our synthesis of methane, we have four hydrogen atoms, each with one electron in its outer shell. Each wants two. Carbon here has 4 electrons in its outer shell. It wants 4 more, or a total of 8 to have a completed outer shell. So it's going to share one of its electrons with each of the 4 hydrogen atoms. So now all 4 hydrogen atoms are happy because they've got 2 electrons in their outer shell. And the carbon atom is happy because it's got a total of 8 electrons in its outer shell. And covalent bonds are often shown in shorthand by a little dash. If it was a double bond, there'll be 2 dashes. Here we have, here's hydrogen, molecular hydrogen, or hydrogen gas. Right? You got 2 hydrogen atoms sharing electrons. Here we have 2 oxygen atoms forming molecular oxygen, sharing 2 pairs of electrons. Right? So a double covalent bond. Okay? I'm going to play this video that basically summarizes what I just said, but it also introduces you to unequal sharing of electrons, which is called a polar covalent bond. This may take a little bit of time. Finally, here we go.
A covalent bond is the sharing of one or more pairs of outer shell electrons by 2 atoms. For example, each of these hydrogen atoms has 1 electron in its outer shell, but needs 2 electrons to complete its outer shell. If the 2 hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as 2 or more atoms held together by covalent bond. An oxygen atom needs 2 electrons to complete its outer shell. 2 oxygen atoms can share 2 pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, 2 shared pairs of electrons. A carbon atom needs 4 electrons to complete its outer shell. It can share electrons with 4 hydrogen atoms, forming a methane molecule containing 4 single covalent bonds. Methane is a compound, a substance formed by the combination of 2 or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs 2 additional electrons to fill its outer shell. Thus, it can form 2 single covalent bonds. An oxygen atom can share electrons with 2 hydrogen atoms, forming a molecule of water containing 2 single covalent bonds. Atoms in a molecule do not always share electrons equally. Oxygen attracts electrons more strongly than does hydrogen. The oxygen atom in a water molecule hogs the electrons, giving oxygen a slight negative charge and leaving the hydrogen atoms with slight positive charges. Because of this, water is a polar molecule.
Okay, so atoms do not always share electrons equally. Okay, so here we have big old oxygen, right? If you look on the periodic table, oxygen has an atomic number of 8. It has 8 protons, right? 8 positively charged particles, which are going to be pulling on these electrons. Hydrogen has an atomic number of 1. It only has 1 proton pulling on those electrons, right? So the electrons are going to spend more time around the oxygen atom than they are around the hydrogen atom. Right? Something like that. So you end up with a molecule with a slight negative charge on the oxygen atom and a slight positive charge on the hydrogen atom. Right? And this is called a polar covalent bond because the molecule is polarized. Now they talk about our society is polarized. You have the the progressives way over here, and then you have the conservatives way over here. I guess that's the opposite. But anyway, you know what I'm saying, right? Because they just have diametrically opposed to one another, right? Well, that's what it means to be a polar molecule. You've got unequal distribution of charges. And this is important because having a polar molecule with unequal charges leads to the formation of hydrogen bonds, which gives water many of its life-sustaining properties, which we will talk about on Monday. Have a great weekend. You had a question? Fats and oil, lipids for the most part are non-polar.
Yeah, I just look like so is ion and just atom
Or gain one. Or gain one. Right? Due to interaction.